So we're going to talk about, this is 20.5, 20.6. Sorry, this is so long and being made. I actually made this once already, and then it didn't work on my iPad, so I'm going to try it here. So, as far as free energy is concerned, well, as far as, I guess, E0 is concerned, which, again, just means your cell voltage or your potential difference, or cell potential. You can call it all kinds of things. But it all means the same thing. It basically means we're measuring it in voltage, okay? So the volts is very closely related to the delta G, which is reaction spontaneity. It can also tell you something about the equilibrium constant, all right? So we're going to talk about all those things today, how all these things are interrelated, which is kind of why electrochem has to be saved for the end, because it ties a bunch of these ideas together kind of nicely. So if you have a redox reaction, then you can relate the delta G to the voltage by this equation, delta G equals negative NFE, okay? Now, that may not make a lot of sense to you. N is the number of moles of electrons being transferred, okay? So you might remember this from the quiz we took the other day. That was a question, how many electrons are being transferred in this redox? That's what you'd have to figure out to get your N. F is the Faraday constant, which is 96,485 coulombs per mole, which can also be stated as 96,485 joules per volt times mole. Now, the reason that's useful, it will come up in a minute because it helps us to cancel some units. But the number 96,485, and I'm pretty sure that that number is, it has been in the past included on your equation sheet. Pretty sure it is also this year. Because they have this equation on your equation sheet, so they would need to tell you what F, the value for F is. Under standard conditions, delta G0 equals negative NF E0, okay? So not any different, you just put the zeros there. Now remember, standard conditions, when we're talking about electrochemistry, it's not just 25 degrees Celsius, 1 atmosphere of pressure. It's also, because we're usually dealing with aqueous solutions, it's also a 1 molar concentration for your solutions if it's going to be standard, okay? So that relates delta G and E, and notice here that the signs are opposite of one another, okay? I think we've talked about this before, but if the voltage is positive for a voltaic cell, that means it's going to happen spontaneously in the forward direction, okay? Now, we've also talked about in the thermodynamics unit that for delta G to be spontaneous, it needs to be negative. It needs to have a negative sign. All right? So you can see how those two have to have opposite signs in order to be spontaneous. So if your E value is positive, that means your delta G value is going to be negative, because these other two numbers, the moles of electrons is always positive. Faraday's constant is always a positive 96,485. So if the E is positive, delta G would have to be negative. And that makes sense because it's spontaneous when E is positive and delta G is negative. And then the reverse is also true, obviously. If the E is negative, then that won't happen spontaneously in the forward direction, and that would make your delta G positive, which would tell us the same thing. All right? So that's that equation. We've got some practice problems here. Using standard reduction potentials in table 20.1, determine whether the following reactions are spontaneous under standard conditions. And I should have had my book open to those reduction potentials. We'll get there. So basically what we've got here is a question of spontaneity. Now we can figure this out in a couple of ways. We could figure it out just using E0, which maybe that's how I want to do this one. You can calculate your E0, and based on what we just talked about, remember, if your E0 is positive, your voltage is positive, and the reason I'm talking about E0, by the way, is because it says we're under standard conditions here. But if your E0 is positive, then that would tell us that's a spontaneous reaction under standard conditions. So there's two ways to do this, really. The first way is just to look at the reduction potential chart, and you can kind of figure it out just by looking. You don't really even have to do a calculation, but then I'll show you the calculation as well, okay? So in this first reaction, reaction A here, copper is going to copper 2+. Because it's becoming more positive, that's an oxidation, right? Lose electrons, oxidation. So then the H plus is going to H2, which is an oxidation state of 0. So that's becoming more negative. So that's your reduction. All right? So then we need to look at our reduction potential chart. Okay? And basically what this is saying is this reaction as it is written, the reduction is going to be the H plus to H2. So that's this reaction is saying that that's going to have a higher tendency to get reduced. So if you look back at your reduction potential chart, it looks like actually copper is above hydrogen on that reduction potential chart. So that shows me right away this is probably not spontaneous as written. Okay? Because that's saying that the hydrogen would get reduced when you put it with the copper, and that's not true. The copper has a higher reduction potential, so it's actually the copper that would get reduced. All right? So you put these two together, the copper and the H plus, and actually nothing's going to happen if you combine it in that way, because the copper can't get any further reduced, right? Copper's not going to have a negative charge typically. So it's just going to sit there. And you actually know this if you think about it, because copper in hydrochloric acid does nothing. We've used copper as a cage in hydrochloric acid before because it doesn't react with it. And that's because when you put copper with H+, it wants to be reduced, not oxidized, and it can't do that. So now, if you put copper 2+, aqueous, like copper chloride or something like that, so you have copper 2+ ions running around in there, and you combine that with hydrogen gas, then you're going to get a reaction, spontaneous reaction, where it forms solid copper, and you end up with H+ in the solution. All right? So that reaction, the reverse reaction, would be spontaneous. Okay? Now, there's another way to think about this, and you could just calculate the E0 for the entire cell using that formula that we had from the other day. E0 of the reduction potential of the cathode minus the reduction potential of the anode. Okay, so then we just have to figure out what is the anode, what is the cathode here. The cathode is the one that is undergoing reduction, okay, red cat. So that would be the H plus going to H2. So if we look at our reduction potential chart, that's actually defined as 0. Remember, hydrogen is kind of our standard. So 0 volts minus the reduction potential of the anode. And as this reaction is written, the anode is the copper because that's what's being oxidized. So if you look at the copper, that's a plus 0.34 volts. Okay. Now just a little quick aside here, just to make sure we understand this from the other day. This is written backwards from what it is in the reduction potential chart, so you're going to be tempted to flip the sign here and make it a negative 0.34 because it's written in the opposite direction. But remember, the equation is the reduction potential of the cathode minus the reduction potential of the anode. So you actually, for the equation to work, you need to use the numbers that are on the chart. You don't ever flip the sign on those numbers when you're working with this equation, okay? So 0 minus 0.34 is going to give us, obviously, negative 0.34 volts, okay? You get a negative voltage, that's not spontaneous. So then we figured it out mathematically, what we kind of already knew in theory, all right? Second one here, we've got the chlorine going to Cl minus, and the I minus changing to I2. So the chlorine is becoming more negative, so that's the one that's getting reduced here. The iodine is becoming more positive, going from a -1 to a 0, so that's the one that's getting oxidized. Okay? So again, we could just look at the reduction potential chart. The chlorine's getting reduced, so in order for that to actually occur spontaneously, that would have to mean that the chlorine is above the iodine on the reduction potential chart. And if you look, it's actually quite a bit above it. Okay, so this one I can already predict is going to be spontaneous. But if you want to work out the math here, the cathode is the chlorine. Okay, so we look at that one. That's a plus 1.36 volts. Subtract the iodine, which is the anode here, and that's going to be 0.54. So that is going to give me 0.82. And that's a positive voltage, so that would be spontaneous. So that kind of confirms our idea here. Okay, next one. Using the standard reduction potentials listed in table 20.1, or use them to calculate the standard free energy change, delta G0, and the equilibrium constant for the reaction. Okay, so now we're going to actually use the two formulas we have here. Delta G0 is equal to negative NFE 0. Because again, we're doing the standard free energy change, okay? And then we're going to do, we might also have to use the delta G equals negative RT ln K. All right? So those are the two equations we'll probably need for this one. The other thing we're going to need to figure out is we're going to need to figure out what is our E0 for this reaction. So we can plug that into the equation and solve for delta G, okay? So first thing we need is the E0 for this cell. And again, that's the cathode minus the anode reduction potential. So we have to figure out which is which here. Silver looks like it's changing its oxidation state. It's going from a 0 to a +1. That's an oxidation because it's losing electrons. Okay. The other thing that looks like it's changing oxidation state is the oxygen. Because the oxygen is a 0 on this side, on the left side. It becomes a 2-, so it's being reduced. It's gaining electrons. All right? So then we need to look at our reduction potential chart here. And again, these will be on the test and on the AP exam. These values will be given to you in the problem itself. You won't have a chart that you have to look at. So that should make it quite a bit easier because then you don't have to go searching for it. They'll just give it to you. The cathode first, that's the one that's being reduced. We need to find the O2 changing into H2O. And that's, in the book, that's about the 5th one down if you're using your chart. I'm not sure exactly which one that is. But it's going to be positive 1.23 for the voltage, minus the anode, which is the Ag plus going to Ag, which is 0.80. Okay, so then when we solve that, that's going to give us 0.43 volts. So that's our E0 that we can plug in up here. Okay, so then we just solve for delta G. So delta G0 is equal to negative N. Okay, so now we got to figure out N. And N, remember, is the moles of electrons being transferred. So we're going to have to work on this a little bit. Let's see. Probably the easiest way, I think, is to look at oxidation state and see how many electrons are being gained or lost. And just pick one thing, right? And then you can confirm it with the other. So looking just at the silver, it looks like there's 4 silver atoms, each with a 0 oxidation state. At the end, you end up with 4 silvers, each with a 1+. So 4 electrons have been transferred here. 4 electrons have been lost in order for that to be the case. Then we can confirm that with the oxygen. Okay, the oxygen starts out with a 0 oxidation state. And then there are 2 oxygens at the end, because of the coefficient 2, that have 2- oxidation states. So again, each of those oxygens would have had to gain 2 electrons. That's a total of 4. So there are 4 electrons being transferred here. Okay. So then we have that 4. Then we've got Faraday's constant here, which, again, if you go back 2 slides, it's 96,485. 96,485. And remember I said we were going to pay attention to the units here. This is in joules per volt times Coulomb. No, joules per volt times mole. Sorry. Okay, so there's Faraday's constant, and then we've got our E0 that we just figured out, which is 0.43 volts. Notice what happens there. The voltage cancels out, okay, and you're going to end up with units of joules per mole here, okay? So your delta G0 is going to end up being negative 1.7 times 10 to the fifth joules per mole. Now that's a big number, and that's not usually how we report delta G. Usually it's in kilojoules, so that would be negative 170 kilojoules per mole, okay? And that's probably a little bit more normal for our delta G. All right, so we found our delta G. Now the second part of what they're asking us here is the equilibrium constant. All right, so now we're going to use this other equation over here. So I'm going to erase this part, but I'm going to keep my delta G number because I need that. All right, so my delta G, whoops, I should plug that in here. My delta G is negative 170 kilojoules per mole. Now I need to be careful because my R here is actually in joules. It's one of the units in my R. So I probably want to go back to this value when I plug it in here, okay? So negative 1.7 times 10 to the fifth joules per mole is equal to, and then I've got to do negative 8.314 joules per mole times Kelvin times my temperature, which is 298 K, times the natural log of K. That's what I'm actually solving for here, okay? After I do my math, work this out, the natural log of K is going to end up being 69. And then we E both sides of this thing to figure out my K. You can probably already tell this is going to be a very large number. So my K is 9 times 10 to the 29th. Okay, so there's my delta G, and there's my K. Now, this should all make sense, okay? The E0 that we found here, I guess I could write that up here as well. The E0 was, 0.43 volts. Okay? So, a positive voltage, a negative delta G, and a really big equilibrium constant. Those things all work together, okay? What that's telling me is this reaction is really spontaneous in the forward direction. Another way of saying that in terms of equilibrium is it's heavily product favored, okay? So that's thus the big K. So again, these all work together. They all should be saying the same thing to you. If you get a positive delta G and a really large K, you probably did something wrong, okay? If you get a negative voltage and a negative delta G, you probably did something wrong, okay? So just pay attention to how all those signs and the sizes, the magnitude of the equilibrium constant should be related to one another, okay? Now the second part of this question I like. I like both parts of it, but the second part is good. It's a good thinking question here. I'll keep my numbers up here so that we can kind of see our values, what they were originally. They're saying, suppose the reaction was written 2Ag plus, and you can kind of go through this, but what you're going to notice is they basically cut the coefficients in half, okay? So they want to know what are the new values of E0, delta G0, and K when the reaction is written like this. So here's the deal. We know that that affects delta G because we've talked already in thermodynamics that the amount of stuff you're using in the chemical reaction is going to affect your delta G, okay? If the amount affects your delta G, it's also going to affect your K. But one thing it's not going to affect is your E0, okay? Because E0, I don't know if you remember this, but the voltage is the same thing as joules per coulomb, all right? So that's voltage. It's kind of the same thing as density, right? Mass over volume. Or, maybe the same thing as molarity, right? Moles over liters. Okay, anytime you have a ratio like that, the amount of stuff you have doesn't really matter. Okay, so if you have a 1 molar solution, that could be 1 mole of solute in 1 liter of solvent. It could be 0.1 moles of solute and 0.1 liters of the solution. Okay, so it's a ratio, and if it's a ratio, that's called an intrinsic property, which means that the amount of stuff is not going to change the value. Okay, so if I decrease the number of moles that I have, now it's kind of important that you realize here we're still at under standard conditions, right? So even if I reduce the number of moles that I have here, this H plus still has to be a 1 molar concentration. This still has to be a 1 molar concentration. This pressure still has to be 1 atmosphere pressure, okay? So we're still under standard conditions, all right? I've just reduced the basically amount of stuff that I have, okay? And if that's the case, then my E0 doesn't change at all because it's an intrinsic property. So this is still my E0 value. Now, for delta G, what's going to change here, if you look at the formula, negative NFE, this is going to change, right? Your number of moles being transferred is now only 2 instead of the original 4. So obviously that's going to cut your delta G in half. Okay, so the new delta G now becomes negative 85, I think, kilojoules per mole. Okay, and because delta G equals negative RT ln K, that's also going to affect our K value if the delta G changes. Okay, less spontaneous means less product favored. Okay, so and I think when you work out the K here, I won't show you all the math for it, but the K ends up being 4 times 10 to the 14th instead. All right. So it's going to decrease the delta G, it's going to decrease the K, but the E stays the same. All right, so I like that question because I think it's good to think about that. All right, Nernst equation. This, again, we're sort of going into the realm of where the AP exam says you don't need to worry about this equation. I really want to talk about this, though, because I think it increases understanding of what's actually going on inside these batteries. Okay, so we're going to go ahead and talk about this. I'll try and stay more on the theory and less on the calculations, but I do want to show you how this is derived, just to kind of show you. So delta G equals delta G0 plus RT ln Q. I don't know if you remember that, but that's how we relate the free energy at non-standard conditions to the free energy under standard conditions. Okay. Now, because delta G is equal to negative NFE, we can just plug that in down here instead of the delta G's, and now we've got something that's related to Q. So now we can relate the voltage at non-standard conditions to the voltage at standard conditions. The reason that's useful is, don't worry about the equation for just a second here, but again, I think I kind of showed you this the other day, but let's say we've got our voltaic cell set up, right? We've got our wire connecting here, we've got these dipped in solution, and let's say this is copper metal, and then this is copper 2 plus inside the solution, this is zinc metal, zinc 2 plus inside the solution. At standard conditions, these are both 1 molar concentrations, okay? Now, the zinc is lower on the reduction potential chart than the copper, so the copper is going to take the electrons from the zinc. So as the electrons are traveling in that direction, they are going to go to this copper 2 plus. The copper 2 plus is going to get reduced and change into solid copper, okay? So basically we're reducing the copper 2 plus concentration in the solution. So over time, that concentration is going to go down. Then the exact opposite is going to happen in the zinc solution because the solid zinc is now losing its electrons, so it's going into the solution as zinc 2 plus, and now this concentration is increasing. So when you have a battery, even if you start at standard conditions, it doesn't stay that way for very long, okay? So this is kind of useful, this whole idea of E, because that tells you the voltage at any given moment in the life of this battery, okay? So a battery eventually is going to end up dying, and we know the batteries die. Now I'm going to explain kind of why that happens, all right? So they're just rearranging the Nernst equation here a little bit. Basically what they have done here is take this, the NFE part, kind of rearrange it, okay? So that you end up with E equals E0 minus RT over NF times the natural log of Q. If you want to do that in terms of log instead of natural log, then that's how you change it. You don't have to worry about these derivations again. I'm just kind of showing you the process here, okay? Now, if we have our temperature at 298, so assuming that we're doing this reaction at a constant temperature, which is a good assumption. I mean, most of the time when we do voltaic cells, the temperature doesn't change, okay? Not always the case, but usually. So if that's at a standard temperature, RT and F all become constants as well, okay? Now, R and F already are constants. And then you got this 2.303 number, so you combine all of that together, and you end up with, whoops, too far. You end up with this thing here, this number, 0.0592, okay? So then you can plug that in instead of the 2.303 RTF, and then you end up with E equals E0 minus 0.0592 over N times the log of Q. Okay, so it gives you less to deal with here. But this is how you can relate your voltage to your voltage at standard conditions, okay? And so then at any given moment, you can look at the concentration of your ions in solution, and you can figure out, okay, what would my voltage be under these particular conditions, all right? So here's an example, just very quickly. Calculate the EMF at 298 generated by the cell described in sample exercise 20.4. So we've got this reaction right here. We don't really need to look back at 20.4 necessarily. But we've got a voltaic cell set up, and notice this is not at standard conditions because the Cr2O72- has a 2 molar concentration. Cr3 plus has a quite a bit lower concentration, all right? So let's just plug into the equation here. We're trying to figure out E, and in order to figure out E, we have to find our E0 first, all right? So let's find E0 for this cell. If we were at standard conditions, what would the voltage be? And that we just do the cathode minus anode thing. So we've got to figure out what is the cathode, what's the anode. I think the easiest thing to see is the anode because the I minus is changing to I2, so that's being oxidized, right? The other one, the Cr2O7 going to Cr3 plus, that's the part that's getting reduced because the chromium is changing from a 6 plus to a 3 plus, okay? So now we know what's getting oxidized, what's getting reduced, so we can look back at our reduction potential chart on this one. And we can see that there it is. The Cr2O72-, the reduction potential is plus 1.33. That's our cathode, minus our anode, which is the iodine, and that's going to be 0.54. Okay, when we figure that out, gives us 0.79 volts. So that's our E0, okay? And then that is minus 0.0592 over N. And we got to figure out what N is. And I think the easiest, again, to look at here is the iodine, and then we can confirm with the chromium. There are 6 iodine atoms. All of them lose 1 electron to become oxidation number of 0. So if you've got 6 iodines all losing 1 electron, that's 6 electrons being transferred, okay? The chromium, you can kind of confirm here. There are 2 chromium atoms on the left side, both at a 6 plus charge. There are 2 on the right, both at a 3 plus charge, so they must have lost 6 electrons. Gained 6 electrons. The iodine lost 6. All right, so there's 6 electrons being transferred, so that's our N, or 6 moles of electrons, however you want to look at it, times the log of Q. Now we've also got to figure out our Q value here. Okay, now remember, Q is basically K, except we're not necessarily at equilibrium. All right, so our Q value is going to be products over reactants. Now what you have to remember is, in our equilibrium expressions or our Q expressions, we only include basically aqueous and gas. Okay, those are the things that we include. So solid and liquid are out. We don't have to worry about those in our equilibrium expression, so we only have one product, that's the Cr3+, and that has a concentration of 1.0 times 10 to the negative fifth. and we have to square it because it has a coefficient 2. Okay, then we divide that by the concentrations of the other three things, the three reactants. Now the Cr2O7 2- is 2.0 molar, and that is, there's just one of those, so we don't really need an exponent there, times the H plus. Kind of nice that that's a 1 molar solution, because 1 to the 14th is still just 1. Okay, we have to take it to the 14th power because the coefficient 14. And then we multiply that by the 1 molar concentration of the I minus. Lost my place there for a second. And that's to the 6th power, but again, it's just 1. All right? So we work all that out. Our Q value becomes 5.0 times 10 to the negative 11. Okay? So then we can just plug that in up here. All right, and we work all that out. Just calculate it. You're going to get a voltage of 0.89. Okay, so that's interesting. We can compare that to the voltage at standard conditions and kind of think about this for a second. Let's talk equilibrium here. All right, so our voltage went up. Now we need to think about whether that makes sense, because basically what we did, from standard conditions, we increased the concentration of a reactant. We took it from 1 molar to 2 molar. And then the other reason this isn't standard is because we decreased the concentration of a product. Now just thinking in terms of Le Chatelier and equilibrium here, if you decrease the concentration of a product, increase the concentration of a reactant, then it pushes the equilibrium to the right. Okay? So it makes sense that our voltage would become more positive here, because now, another way to say that is, it is now more spontaneous in the forward direction. Okay? So that should make sense to you. Okay? Now, obviously, so basically, you should be able to now look at this, and you should be able to get an idea of what would happen to your voltage if you raise or lower the concentration from the standard. Okay? And you don't necessarily have to be thinking about the Nernst equation to do that, which is why they say they want you to think about it in theory, but they don't care if you calculate it. Okay? But I thought maybe going through one of the calculations would just be helpful for you to see how it all works. Now, the other thing to think about here, remember that delta G is equal to NFE. So now we're not at standard conditions, right? If you remember this from thermodynamics, when a reaction reaches equilibrium, which this reaction is striving for equilibrium eventually, okay? Your delta G is going to end up being 0, okay? Sorry, there should be a negative sign here, negative NFE. If your delta G is 0, and you solve for E, then your E is also 0, right? 0 divided by anything is 0. So at the point at which we reach equilibrium for this reaction, your E value is at 0. Okay, there's no more voltage flowing through there. So a dead battery is a battery at equilibrium. Okay. Now another way to think about this, this reaction is, it has a positive voltage, so we can say that it's very spontaneous in the forward direction, which tells me that it has a big K. Now, we don't know what that K is. We could calculate the K. Because we know the voltage, we could actually go ahead and calculate the K from the voltage, right? We don't need to do that on this one necessarily. But let's say that the K, I'm just going to make up a number here, 1.0 times 10 to the 20th, is that, let's say that's our K value for this one, all right? This is our Q value at this particular point, okay? So obviously our Q is very far away from K, and that tells us again this reaction would need to shift to the right in order for Q to get to K, all right? Once Q is at K, now delta G is 0, the reaction stops. Okay, the only way to start it back up again is to apply some energy to push it back against the grain so that it's now not at equilibrium anymore, okay? And then the reaction will start trying for equilibrium again, okay? And you can go back and forth on that with a rechargeable battery. So hopefully that kind of makes sense for you. The chemical process that is taking place in the battery, we're going to start talking about that more in the next few days, but I just wanted you to have that background here about how all of those things relate to one another, because I think that's a really important concept to understand. Okay? All right, I think that's it. There is this idea of concentration cells. I'm not too worried about that, but the Nernst equation does show that you could create a cell with the same substance at both electrodes, just with different concentrations. All right? So what they're showing here is a nickel concentration in one solution of 1 times 10 to the negative third, and then standard concentration in the other one. Okay? So because you have that difference of concentration, you're actually using the exact same things, but because you have this concentration difference, there will be a voltage, right? There's a flow of electrons from one side to the other just because of the difference in concentration. So you can create something called a concentration cell just based on that difference. Now eventually, again, it's going to get to equilibrium once the concentrations are the same on both sides, right? We're not going to worry about a calculation or anything with that. I just wanted to mention it. For such a cell, E0 of the cell would be 0, but Q would not. Okay, so as long as the concentrations are different, E will not be 0. Okay, again, E0 would be 0 because for E0 you're calculating if they're both at 1 molar concentrations, which they're not here. Okay, that's kind of the idea, is that this thing is not at standard conditions because one of the concentrations is different than one. At least one of them is different than one. Okay. So as long as the concentrations are different, the E will not be 0, but as soon as the concentrations are the same, then the E would change to 0 at that point. Okay? So that's it. We're going to start talking about batteries the next time we have a video. See you in class.